Hello everybody, we are in week 4 of this particular course. In this class and also in the next class we shall discuss multiplexer. And in this class we shall cover multiplexer basics and how to get a higher order multiplexer from lower order and its relation to Shannon's expansion theorem. Before that, let us have a quick recap of what we discussed in week 3. We saw that Karnaugh map is useful for simplification, but when it becomes 5 variable, we need a 3D visualization, and more than 4 variable it is difficult to using Karnaugh map. And if we use entered variable map, the map size reduces by a factor of 2. And QM algorithm, when we have more number of variables, QM algorithm is useful and we can generate a computer based algorithm, a code for minimization. And when we look at various realization of a logic circuit, digital logic circuit, we consider certain cost criteria, which could be get input cost, total number of or literal cost, or a total number of get inputs plus total number of gates that are used. So using those gate criteria, we can think of minimizing one particular function, and of various options we can select one particular option. And when we have to realize multiple function, then we can see how we can use the shared terms that could be there amongst multiple functions. And during realization, when we are doing the minimization, due to finite propagation delay, there could be glitches that can occur during the transition from one particular value to another, and such potential glitch in a circuit gives rise to hazard, and to cover hazard we need to include additional terms which is considered otherwise redundant. So this is briefly what we discussed in the last week. So to discuss multiplexer, we look at a truth table which is converted to a Karnaugh map realization, which is what you see over here. This is something which we have seen before, very simple. Okay, the truth table is like this. Okay, and what is this truth table saying? If when A is 0, right? So the output here follows C. You can see 0, 0. C is 0, Y is 0. C is 1, Y is 1. As long as A is 0, and when A is 1, output follows B. So this is 0, this is 0, this is 1, and this is 1. Very simple truth table corresponding Karnaugh map, and this is the realization. And corresponding hardware realization converted this particular logic equation is what you see over here. Now this one can be seen in a different way, the way we look at the algorithms. So if A means if A is true, if that is if A is equal to 1, then Y is equal to B, isn't it? If A is equal to 1, this term becomes 0 dot C, which is 0, and this terms becomes 1 dot B, which is B. So Y is equal to B. So we can write this way: when A is equal to 1, okay, Y is equal to B, right? Else means when A is not equal to 1. The other option, this is a binary, possibility of 0 and 1 only is there for the variable A. Okay. So when A is 0, so what we see? This is 0, 1 dot C, and this is 0 dot B. Okay. So in that case, the output is only C. So for A is equal to 0, output is C. So we can write the truth table in this manner also, and this is the corresponding meaning in terms of the codes that we write for algorithms. Okay. Now, how is it related to multiplexing operation? So for that we define what is a multiplexer. A multiplexer steers one of the many inputs to an output based on what the control input says. Okay, this is what is the job of a multiplexer. So here there is an example where which is doing a 2 to 1 multiplexing. That means 2 inputs are there and 1 output is there. We shall see example of 4 to 1 and 8 to 1 and other things. So this is the transmission line, say, and these inputs is not required to transmit every point of time. So when at certain point of time D wants to transmit, at some other point of time D1 wants to transmit. So there is no need of putting a dedicated channel for each of D0 and D1, because this channel is very long. It will accordingly the cost gets increased. So here one channel can be used by both D0 and D1 depending on the need, and how it is decided who will take control over the transmission channel, that is the Y. It is decided by S0. So when S0 is 0, D0 gets connected to Y, and when S0 is equal to 1, D1 gets connected to Y. So that is the idea. Is it okay? So if there are 4 such things, then there will be 4 such inputs, and then the select lines will be accordingly, which we shall see later, right? So this particular thing and what we just discussed in the previous slide, you can see there is a similarity. So here what we are looking at, in this case we are looking at an expression which is something like this. So when S0 is equal to 0, Y is equal to D0, and when S0 is equal to 1, Y is equal to D1. This is similar to this relationship. Okay? So the same circuit in which what we had seen for A, if we assign that to S0, that is a select input, and B and C becomes data inputs, which is given to D1 and D0 respectively, then the previous circuit behaves like a 2 to 1 multiplexer, okay, where A is your S0, D0 is your C, and D1 is your B. Okay? The same circuit, same hardware realization that we had seen. Okay? And then we can represent it in the form of a block. Okay? So this is the block within which that hardware, the hardware that we had seen before, is there. Okay? 2 AND gate and 1 OR gate. So this S0, when it is 0, this is the control input, D0 is actually getting connected to Y. When S0 is equal to 1, D1 is getting connected to Y, right. So that is the idea, and this is the way a simplified block level representation is made, and we can make use of this block in subsequent discussion, knowing that inside the block there is a the hardware that we had seen before with 2 AND gate and 1 OR gate. That is what makes a 2 to 1 multiplexer. Now we look at 4 to 1 multiplexer. Okay. So 4 to 1 multiplexer, as per our previous understanding, there will be 4 data inputs. So D0, D1, D2, D3, this is the way we designate them, and this is one output, right? And one of them will get access to Y depending on the select inputs. Again, these S1 and S0 are binary variables. So for selecting 4 of them, we need 2 of them, 2 select lines. So when S1 and S0 are 0 and 0, D0 is getting selected. That means Y is equal to D0, right? When they are 0, 1, D1, when 1, 0, D2, and when 1, 1, this is D3. Okay. So how do we write it in the form of a logic equation? So this is the way we can write it, right? So when we substitute S1 and S0 as 0 and 0, both of them are 0. So this is 0 prime, that is 1, and this is 1, and this is D0. And rest of the term, 1 of S1 or S0 will, for being 0, will generate a 0. So plus 0, plus 0, plus 0. Okay. So Y is nothing but D0. So for S1 is equal to 0 and S0 is equal to 1, this is the term associated with D1, which will be the value of Y, and the other terms will be this term, this term, this term, this 3 term will be 0. So this is how we can write the expression. Okay. And the corresponding hardware is what you see over here. So S1 and S0, right. So amongst them these 4 possibilities are there. So 3 input AND gates. So these are the selections, and this is D0, D1, D2, D3. So if it is 0, 0, so this is 0, So this becomes 1, this becomes 1, and this is D naught. So y is equal to D naught at that time, and rest of the values these AND gates at that time will be 0 only. This is D naught, okay, for S1 and S0 at 0. So similarly for other values also you can check, and you can see that the output is following this particular truth table. Okay. So 4 to 1 multiplexer, when we give a block diagram representation, so this is the block diagram representation, 2 select inputs S1 and S0 and 4 data inputs, these are the 4 data inputs, and there is 1 output, and 2 select inputs, the first one is S1 and the second one designates S0. Okay. So 0 0 0 1 1 0 1 1 and corresponding inputs are assigned here, and this is getting connected to Y depending on the S1 and S0 value. So what is there inside this block? This hardware is there. Okay, this hardware is there, this particular logic circuit is there, right. So when we use this as a block, we know that inside this is the logic circuit that is there. Clear? Now let us look at the 4 to 1 multiplexer equation a bit closely. So this was the basic equation we had seen before. Now if we take S1 prime common between these two, right, so we get S0 prime D0 and S0 D1, and if we take S1 common between these two, we get S1 out and S0 prime D2 and S0 D3, okay, within the bracketed term. Now if you look closely at these two, this particular term, these particular two terms, SOP term, what is it? It is nothing but a 2 to 1 multiplexer equation, okay. And what is this? This is also a 2 to 1 multiplexer. So basically you have got this realized by a 2 to 1 multiplexer, and this is realized by another 2 to 1 multiplexer. And if you write this particular function as F0 and this one as F1, you have got S1 prime F0 and S1 F1. This again is a 2 to 1 multiplexer equation where F0 is your D0 and F1 is your D1, the basic equation if you remember. Okay. So essentially in the 4 to 1 multiplexer, if you see, right, there is one 2 to 1 multiplexer, one 2 to 1 multiplexer, and finally another 2 to 1 multiplexer. So 3 2 to 1 multiplexers are there. So if you write it in the terms of 2 to 1 multiplexer, so this is how what we can see this particular equation getting manifested in the form of hardware realization. Inside you have got 2 to 1 multiplexer circuit the way we have seen before. Okay. So when S1 is say 0 and S0 is 0, what is happening? S1 0 means F0 is selected at the output, and when S0 is 0, D0 is selected as F0. Okay. So at that time, then when S0 is 0, this is D0 is your F0, F0 is equal to D0, and Y is equal to F0 is nothing but D0. So this line will be going there, and if it is instead S1 is 1 and S0 is 0, so S1 is 1 is this line will be selected, F1 will be selected, S0 is equal to 0 means this one will be selected. Okay. So F1 will become D2 at that time, right, and Y will become F1 equal to D2. So basically we are having this line going to output for S1 is equal to 1 and S0 is equal to 0. Is it clear? So we can see that this way higher order multiplexer can be obtained from lower order multiplexer in a so there is a generalized approach for this. So the earlier one was 4 to 1 multiplexer was obtained from 3 2 to 1 multiplexer. Now let us look at the example of getting 8 to 1 multiplexer from lower order multiplexer. So 8 to 1 multiplexer, how many selected inputs will be there? 8 inputs. So selected inputs will be with 3 select inputs we can get 2 to the power, with 3 select inputs we can get 2 to the power 3 up to 8 input line getting selected, okay, and getting connected to the output, steered to the output, right. So, 3 inputs are 3 select inputs are there, and these are D0 to D7, these are the data inputs, and the S2, S1, S0, that is the 0, 0, 0. So, this is the corresponding data input. D0 is getting connected when they are 0, 0, 0. So, any other value, say 1, 0, 1, 1, 0, 1. So, D5 will get connected to Y. So, this is the understanding, right. And how we can get it? This for 8 to 1 multiplexer from lower order. So, we can have 2 4 to 1 multiplexer. We can have 2 4 to 1 multiplexer the similar way, the way we have expanded the equation before. We can go go with the same exercise. So, this is 1 4 to 1 multiplexer, and this is another 4 to 1 multiplexer with S1 and S0, right, which is generating F0 or F0 and F1 two functions, and S2 is a 2 to 1 multiplexer which is selecting which of this F0 or F1 will be going to the output, and F0 and F1 will take one of these input values depending on S1 and S0 that is there. So, again we take the example of say S2, S1, S0 as 0, 0, 0. So, S2 0 means F0 will be selected, right, and S1, S0 0, 0 means D0 will be selected, right. So, this is the path that will be there. Okay. So, if we take an example of S2, S1, S0 as 1, 0, 1, what will happen? S2 is equal to 1. So, basically F1 will be selected, this one will be selected as going to the output, right. So, y is equal to F1 will be there, and this is 0, 1, S1 is this is 0 and this is 1. Okay. So, 0, 1 is, so this is the one, D5 will be selected. So, F1 will become D5. So, y is equal to F1 is equal to D5. So, D5 will go to the output, absolutely no issue. So, this is what you can see happening when you have got higher order multiplexer realized by lower order. Now, imagine a situation when you have got in the store only 4 to 1 multiplexer, you do not have 2 to 1 multiplexer, right. So, can we realize it? Of course, because we can always get a lower order multiplexer from a higher order. Getting higher order from lower order, we have to follow a cascaded approach, stage by stage approach, the one that we have seen now, and to get a lower order from higher order. So, this is one example where we are getting a 2 to 1 multiplexer from a 4 to 1 multiplexer. What we are doing? So, there are 2 select inputs, we just have made common. So, S2 is connected over here. So, whenever we place 0, both the select inputs becomes 0. Okay. So, this will be selected, and when we place 1, so these 2 become 1. So, one of this one will be selected. So, either this gets selected or this gets selected, right. So, one of either this input goes to the output or this input goes to the output. So, this is nothing but 2 to 1 multiplexing, one of these 2 going to the output. Okay. So, we can replace this block with this one, okay, and accordingly we can get the 8 to 1 multiplexer using only 4 to 1 multiplexer. Otherwise, 2 4 to 1 multiplexer, 1 2 to 1 multiplexer is sufficient. Now, in the previous example, we had seen 2 4 to 1 multiplexer getting connected to 1 2 to 1 multiplexer to give you ultimately a 1 8 to 1 multiplexer. And before that, we had seen that 4 to 1 multiplexer can be obtained by 3 2 to 1 multiplexer. So, this is 1 4 to 1 multiplexer that we had seen before, okay, which we can replace with 3 2 to 1 multiplexer, and this is another one which can be replaced with another 3 to 1 multiplexer. So, this is essentially a 4 to 1 multiplexer, okay, and finally, this is a 2 to 1 multiplexer. So, ultimately how many 2 to 1 multiplexer we can use to get the 8 to 1 multiplexer? 1, 2, 3, 4, 5, 6, 7. So, with 7 2 to 1 multiplexer, we can get 1 8 to 1 multiplexer realized. Okay. So, this is one thing that we can take note of, that we can go up to that level. We can further break a 4 to 1 multiplexer to 2 to 1 multiplexer and realize it. Okay. And this is one example where a 32 to 1 multiplexer is obtained from a from 16 to 1 multiplexer and 2 to 1 multiplexer. So, two 16 to 1 multiplexer are there, they are generating two output like the one that is there before, and one 2 to 1 multiplexer is combining these two outputs and is generating output. So, these are different examples by which I hope it is clear from to you that how higher order multiplexer can be obtained from lower order, and also we have seen how lower order can be obtained from a higher order. Okay. Now, we shall look into Shannon's expansion theorem and its use in the multiplexer design. So, Shannon's expansion theorem, we are revisiting it, we have seen it before. Okay. So, Shannon's expansion theorem, this is the one. Okay. You remember this one. So, given any function f x1, this is the number of variables, I mean it could be 3 variable, 4 variable, 2 variable, I mean just it is a generalized expression. So, x1 prime, so corresponding term x, wherever x1 is there it becomes 0, ANDed with the function x1 prime replaced by 0 plus ORed with x1 and the function wherever x1 is there you replace it with 1, whatever comes up. So, you just simply sum these two particular products, you get the original function. So, this is Shannon's expansion theorem which you have seen before. Now, in the 2 to 1 multiplexer context, we can see if this is my x1 and this is the select inputs. So, for 0 1 will go and for 1 the other will go as output. So, if this is my y, this is y, then if x1 is 0, this is the term that is going, this is my corresponding d0 equivalent to d0, right. And when x1 is equal to 1, this one will go to the output because x1 is equal to 1 means this term will become 0, the top term will become 0. Okay. So, the output will become this particular expression, okay, which was d1 before. So, there is a inherent if then else, if x1 then f1 x2 x3 to xn this particular function, and if not x1 else, that is then f0 x2 x3 to x1 this particular expression will be the function output. Okay. This is similar to the multiplexing action that we see. Okay. And this we can look at, we can put it into the basic multiplexer, say 4 to 1 multiplexer equation, and for S1 taken out as x1, wherever S1 is appearing we can put 0, 0, 0, 0, and the other one S1, this was S1 prime, wherever S1 is there we put 1, 1, 1, 1, and then we simplify, we see that we get back to what we had seen before. So, this is one 2 to 1 multiplexer equation giving f0, this is another 2 to 1 multiplexer equation giving f1, and finally these two are getting combined, this is your the third 2 to 1 multiplexer. So, similar, exactly similar to what we had seen earlier. And we also note that the Shannon's expansion theorem can be nested. So, first you take x1 out, so whatever you get this specific equation, you can take x2 out, right. So, by which you can write this expression and the other expression, and similarly you can look at this expression, so x1, so you can take x2 out, so x2 prime here and x2 over here. So, this one wherever x2 appears, in this case when x2 prime is taken out, so 0 will be there, and when x2 is there, x1 will be there. So, this is the nested version of the Shannon's expansion theorem which you have seen before. Okay. And so, this is equally applicable over here, right. And if you do that, the earlier 8 to 1 multiplexer realization, the one that we had seen using 2 to 1 multiplexers, right. By nesting, what we can see is shown in this particular diagram. So, this is your FABC, right, the basic equation. So, A is your select input. So, whenever A is 0, right, this one is going as the input, and whenever A is 1, this one is the input, okay, right. Now, this F0BC, this is the output of another 2 to 1 multiplexer. So, whenever this is the B, wherever B, the first one, whenever B is equal to 0, we put this as F00C will be the input, and whenever B is equal to 1, F01C will be the input. Okay. Similarly, there will be the other line. And finally, this F00C, if C is taken as the select input out, so these 00 terms are there. So, C is equal to 0 is this term and C is equal to 1 is this term. So, accordingly, we have these 8 possibilities, F0002, F111 is over here, and the individual outputs that are generated at every level, this follows the Shannon's expansion theorem, the nested version that we had seen in each of these cases. Okay. And this we can see over here also, right. And for any value, say A, B, C, we have already noted this particular term. So, if we have a function that we want to realize using this particular multiplexing architecture. So, this ABC, and this is, say this is the corresponding truth table. Okay. So, wherever there is a 1 in the truth table, right. So, F ABC F000, so this is my F000, right. So, if there is a 1, so there is a 1 over here, so we put corresponding D0 value as 1, 001. So, this is the corresponding term, we see the truth table output in this particular place is 0. So, this is the corresponding input. Okay. So, we put D1 as 0. Okay. So, this shows that using multiplexer we can realize a truth table. So, inside this is what? This whole block is 8 to 1 multiplexer. We have realized it in this manner, right. But effectively this is a 8 to 1 multiplexer. So, if input to that is F000 to F111 over here, okay, this can map to the truth table by appropriately placing the values of D0, D1, D2, D3 up to D7, okay, making them zeros and ones as per the truth table DOA we have seen it. More of this we will see in the next class of the multiplexer. So, to summarize, multiplexer steers one of the many inputs to an output based on control inputs. N control inputs can select up to 2 to the power n data inputs and steer it towards the output. Higher order multiplexer can be obtained from lower order by cascading. Lower order multiplexer can be obtained from higher order by appropriate connection of select inputs. And Shannon's expansion theorem and its inherent if then else structure is useful in getting insights of multiplexer operation. Thank you.